So in this video, we're going to practice converting back and forth between double Newman projections and chair structures using the steps I described in a previous lecture. So should be some nice practice is the hope, at least. Okay, so let's take an example and we're gonna answer the question or complete the task, however you wanna phrase it, of drawing a double Newman projection from a chair structure. So draw the corresponding double Newman projection. Okay, so the chair structure looks like this. Let's get a really hard one. Just to show you that if you have some semblance of understanding single Newman projections, double Newman projections aren't too bad. Okay, so we want to go from here to here. That's the question. Okay, so the first thing I'm going to do is redraw my chair structure nice and big. And I guess in the problem, I should have provided some eyes. That's probably something I will do so that the answers, because there's so many different answers for this, and it gets to be kind of tedious to grade if I have to rotate the molecule in my mind. So I would probably provide the eyes for us, suggesting that we're going to look down and analyze this bond and this bond in the original problem, although I wouldn't have provided that in the original problem. That would be something that you would have to draw, so, or identify. So let's make sure we're clear as to what I would provide. All right, let me finish adding the groups. Okay, so we have an equatorial OH, an axial chlorine, an equatorial fluorine, and then two axial methyl groups in the molecule. Our eyes are looking, they're positioned on the left, they're looking right. As we're looking right, and the first carbon that our lower eye looks at is a dot, the second carbon's a circle. Our higher eye looks at a dot with the OH and then a circle up here with the chlorine atom. Okay, as we correspond or transfer this over to two dots with circles around it, first thing we have to do is figure out whether the left and right eyes correspond to the yellow or purple magentas. We need to be able to go kind of back and forth between there. So the first thing that we know is that if we're looking right, the lower / wedge is right. And then conversely, if we're looking left, the lower or wedged carbons or eye is to the left. Okay, so we're looking right, the lower eye is on the right. And so that's going to mean that if we use this purple, however you want to do it, our purple schematic, we're going to have our right eye be purple, magenta, whatever. The left eye is going to be yellow. Now, how are our dots connected? Our dots are connected by an up flap. Our dots are connected by an up flap. Let's draw that in our Newman projection. Our circles are connected by a flap that's pointing downwards. So we just have a down flap connecting the circles to each other. And that's going to define the blanks that we will fill in with the appropriate groups. So here, 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 here. Okay. So now we have the schematic for our double Newman projection built. We know which side is left and right on the chair structure. We know we've connected everything appropriately with the correct facing flaps. We've added the missing groups, we've added the blanks to tell us where the missing groups will be. Okay, so now we just kind of, at this point, we're all set up. What we do is we identify on the purple side, we have a dot. Okay, I'm trying to, maybe I'll do this. Star on the purple corresponds to the purple dot. Now what's attached to that purple dot? Well, there's this one carbon down here, okay? And it's just a line. It's just shown as a CH3 group as a line pointing straight downwards and axial. Well, now if you go over to the starred carbon over here and the dot for our double Newman projection, which of the two missing groups, the one pointing up and to the left or the one pointing straight down, is going to correspond to the carbon that's pointing straight down in our chair structure? Well, these things are supposed to match. And so what we would say is that if we drew the CH3 more explicitly, let me just do that. I'm just going to have this line going straight down. I'm going to write CH3. That CH3 that's pointing straight down in our chair structure is still going to be pointing straight down in our double Newman projection. You see, the groups that are pointing straight up and straight down are our axial groups. It doesn't matter if they're in the double Newman projection or the chair structure. Straight up and straight down is axial. More diagonally horizontal is equatorial, chair structure or double Newman projection. Now we do have to fill in the blank on our double Newman projection, so we have to write in the H as we did before. Now you could go over to the yellow dot or you could go back to the purple circle. If you go to the purple circle, you notice there's nothing there. Well, there is stuff there. It's two hydrogen atoms that they're drawn, their existence is implied. We don't have to draw them explicitly if we're drawing a bond line structure, which is all that a chair structure is, a perspective bond line. But in our double Newman, we do need to include them. So I'm going to write in the axial H and the equatorial H of our double Newman projection. Okay, now over to the dot on the yellow side, which corresponds to the dot over here. Maybe I'll draw a rectangle just to help guide your eyes a little bit. That OH is in a really tough position if you're not comfortable with chair structures yet. Is it equatorial or is it axial? It is in fact equatorial. It's just the most, and maybe it's on me, maybe I need to make my flap a little bit more pronounced, but it is an equatorial that's the most difficult to kind of visualize, but it is equatorial. So if you're not sure though, if you look at the double Newman projection at the squared carbon, I'm kind of coloring in here. At this dot, we could go up and to the left or straight down. Now, there's no way that that OH should be put in the down position, right? I mean, it doesn't look like it's anywhere near straight down. As far as diagonally and up and to the left, that looks a little bit more plausible. So I'm gonna put my OH there, and that is now an equatorial group. So we see our equatorial positions are more diagonal, and maybe even a little bit easier to see in the double Newman projection than they are in the chair structure. And then we have an H pointing straight down that we can't forget about. Going back to the circle on the yellow side, we see a chlorine atom. So we have a chlorine atom. Is that chlorine atom pointing straight up axial? Yes. And so when we go to the circle on the example, we'll see that the chlorine goes straight up or axial. We have to fill in the blank and add the hydrogen atom. We're done, right? Well, no. What about these groups? This methyl and this fluorine. The fluorine's equatorial, the methyl is axial. How do I depict those as a double Newman projection? And you can't. The double Newman projection is set out to accomplish the task of analyzing the conformational state of two bonds in the chair structure that happen to be parallel to each other. The magenta and the yellow lines in our chair structure are parallel to each other, and they are the ones that we can analyze productively using a Newman projection. Because we can do both at the same time, let's make it a double Newman projection, connect things with flaps. Anyway, we've been there. But the flaps themselves and the groups that are attached to the flaps cannot be accurately depicted using a double Newman projection. It's a limitation of double Newman projections. You can't do it. So, but what you can do is say, okay, those magenta or whatever, I'm sorry, that color of fluorine or methyl, in methyl group looks orangish to me. I don't know. Are they on the flap closest to our eyes and closest to the dots, or the flap that's connecting the circles? And indeed, they are on the flap that's connecting the circles to each other, that down flap. And so what I would just do is I would go over to that flap, draw two lines, one for a fluorine atom, and you could add a CH3 here if you wanted. You treat the flaps like bond line structures, okay? You don't worry about dots and circles and that sort of thing. You just draw what's attached to them. So What we've done is we've drawn a really complicated double Newman projection from a fairly complicated chair structure. So we've gone from the chair structure to the double Newman projection. And then maybe an interesting question is to ask, can we go back? Can we go back, that is, from double Newman to chair? The answer is sort of. It's not really that productive. So yes, in some cases, and you really don't want to, okay? You generally just start with a chair structure and go to a double Newman. It's just not a thing to go from a double Newman back to a chair structure. And the reason why is because so much information is lost at the flaps of a double Newman projection. So for us, we're not going to worry about it. I just want you all to be able to go from the double Newman to the chair structure. It's just not one of these things that anybody will ever pay you for it. You sit down and go through a bunch of double Newman projections. And again, the reason why is related to this orange group. So the orange groups in the double Newman projection shown up here, if we started with the double Newman projection and had to go back to the chair, we would know where to put the fluorine in CH3. They'd go at that carbon on the right flap that's pointing downwards, but I cannot tell from the double Newman projection whether the fluorine is equatorial or axial, so I wouldn't be able to draw an unambiguous structure. There would be some ambiguity, and it just makes it so it's not really all that worth it. But anyway, so that is going from a chair structure to a double Newman projection. That's all you're required to do, in addition to knowing how to interpret double Newman projections, but you don't have to worry about having to go from the double Newman back to a chair.